Hello everyone, welcome to Chapter 4, Section 2, Exponential Functions. Sorry if I sound a little funny right now. I am slightly congested recovering from a cold, so please bear with me on that, okay? So, topic for this section is, of course, exponential functions, and we start by defining what an exponent is and how we operated with rational exponents, which were fractional exponents, right? And we said, hey, remember that if you have a to the m over n power, you would get, that is the nth root of a to the m. And you can actually interchange that order. Those both mean the same thing. So that we had this nice example, 16 to the 3/4 power, which is the fourth root of 16 cubed. And the fourth root of 16 is, of course, 2, and so 2 cubed is 8. And so there are a few examples worked out here for you, showing you some different ways that you might see an exponent worked out, all right? And so in this section, we actually go further. We can use any number, not just a rational. We can even use irrational numbers to be the exponent of a value. And there are some techniques we use to approximate what that is, but for the most part, we're not going into how to approximate what like 2 to the pi power is, right? There are ways to approximate what it is, but we're not trying to go that deep into it, okay? So we'll start with some bonus properties of exponents here. And most of these are logical extensions of the basic properties that you know, but a few of them may not be obvious at first glance. So we'll just briefly talk about these four properties that they've given us. So first, a to the x is a unique real number for all real numbers of x. Basically, you can never get the same answer from two different exponents on a base, right? So if it's 2 to the 4th is equal to 16, you're never going to have 2 to some other number also equals 16, okay? And they kind of give us some helpful explanation on the right-hand side where they say a to the x can be considered a function with a domain of all real numbers, okay? And then part B, they say a to the b equals a to the c only if b and c are equal, right? They say if and only if, but specifically that means that if you have the same base and you want to put it equal to something, those exponents are going to be equal. This is a very helpful technique for solving certain equations, so we'll see that as we progress. The third one is that increasing an exponent generally leads to a larger number, and part D is, of course, the opposite of that, which is if you have a fractional base, then your function is a decreasing function. So increasing your exponent causes the value to adjust based on the base. A whole number base will lead you to a increasing function, which we sometimes refer to as exponential growth, right? And then on the other hand, if you have a fractional exponent, we sometimes call that one exponential decay. Okay, so two different versions. They still have a lot of similar properties. However, one of the functions is increasing because it has a base that leads it to grow, and the other one is decreasing. Okay, so let's delve into exponential functions a little bit, and let's take f of x is a to the x power, where a is some base number that we're going to operate from. And in our example, we use 2 as that value, right? So they said if a is greater than 0 and a does not equal 1, right? So basically, you need some number. If you put it equal to 1, your entire function's a constant, not really super helpful or interesting to study. And so we're now going to study this case where we have some base number and our independent variable x is actually in the exponent of our function. So taking a look at example 1, we've got 2 to the x power as our base function. And what we're going to do is we'll just look at what happens when we plug in certain numbers. So first case, f of -1, that would be 2 to the -1 power, which is actually just 1 over 2. Remember, an exponent, when it is negative, causes your fraction to flip, and this would just move that 2 to the opposite side. Okay? Let's keep sliding along and see f of 3. Okay, so this is 2 to the 3rd power. And if you just do, well, 2 times 2 times 2, that's just 8. Okay, so simple enough, that one. Nothing super duper fancy there, okay? And now we get to some of the fun ones here, where we've got 5 over 2. So 2 to the 5 over 2 power. Well, now this is where things get creative. We're like, well, what do we do with this? Okay, well, let's start with this. Let's break this up into 2 sections. Let's start with 2 to the 5th, and then 1/2 power of that, okay? And so 2 to the 5th, we can multiply that. That is 32, and it's going to go to the 1/2 power. Now, a 1/2 power is actually just a square root. And we can now also simplify this square root, and I'm just going to point this out. 32 is 16 times 2, which the square root of 16 times the square root of 2, which is 4 root 2, okay? And so basically we simplify this root to get this as our final answer. So 2 to the 5 over 2 power is actually 4 square root 2. Really interesting how that path kind of leads us there, but logically it does make sense when we work it all out, right? And then we've got part D. Now this one is 2 to the 4.92 power. Well, okay, how do we do this? A couple of things. Well, we're not trying to go deep into number theory and see how we would approximate this. The simple answer is just plug this in your calculator, okay? What normally the way it would work is we would do something like this. So I'll show you just so that we can kind of be exposed to some things. We would do 2 to the 492 power and take the 100th root of that, right? But instead, what I'll say is don't actually try to calculate that out. Just using a calculator, plug this in, and you'll get that it is 30.2738. It continues on for a while. Okay. And the key thing is, like, we could approximate this using some more advanced math techniques if we wanted to really delve into it. It is still kind of an interesting thought, though, like saying, hey, we could write this as 2 to the 492nd power with a 100th root on it, right? And it's just kind of something to think about, but not something we really want to go and explore in this single topic, okay? So that's the basics of just computing some numbers with different exponents. Some of this should be pretty familiar back to when we talked about laws of exponents and some of our review chapter work. Okay, so let's delve a little bit into the exponential as a function. And so this is actually broken up into 2 pieces. So first, there is the exponential growth version, which is actually this first box. So I'll just label that this is growth. Okay. And the second version of this, which is sometimes referred to as decay. Okay. So decay, where the value is decreasing, that's because your base is a fraction. And in the first case, you would see that your base is a whole number. And that's how we kind of can differentiate these two. Now, they do have some commonalities, okay? And that is the 3 main points that our parent graph passes through. There is 0, 1, 1a, and -1, and the reciprocal of a, okay? And that's true for both of these groups. You can see that. The functions go in different directions, but they have some similarity in their behavior and in their points. What you'll notice is this example, of course, uses 2 and 1/2 as their base, exact reciprocals. And you'll see kind of like, wait a minute, yeah, where I have 1, 2 up here, the decay version has -1, 2. And one cool thing what you'll discover is if you look at this bottom piece, okay, there is this little bit of information where they say, like, well, 2 to the -x is actually the same thing as 1/2 to the x power. Like, these both, in mathematical sense, mean the same thing. And the only difference between the decay and a growth is literally just a reflection over the y-axis. Okay, and that's kind of what they said in this line right here. So that's some interesting points about it. Some key things to remember. Remember that 0, 1 is always that y-intercept for a basic exponential function. And then 1a and -1 reciprocal a will be points on there. Okay, that'll come up when we do some graphing with these. Okay, so let's graph some exponentials. and they just started with something simple. They gave us a few points to remember, which is just the three main points that we use to graph an exponential. There's always a horizontal asymptote, which starts at the x-axis. Remember, if you shift your graph up or down, it'll do that. And then a little reminder about domain and range. Okay, so this graph is pretty simple. There's no transformations or anything on it. It's just got a base of 1/5, okay? So what we'll do is let's come up with our 3 points. The simplest point, of course, being the middle point, which is 0, 1, okay? And we're also going to have what they said is -1, 1 over a, my base, which is actually 1/5 in this case. So this is like 1 over 1/5. A little bit of a weird point, and I'll simplify it in a second. And the last point, of course, is 1, a, 1/5. So here's where we're kind of at. We've got this -1, 5, 0, 1, and then 1, 1/5. Okay, so let's plot these. I'll also go ahead and mark my horizontal asymptote, which is at 0. So this is my horizontal asymptote. Right, we'll say y equals 0. All right, let's graph these points and see what we get. So we've got 0, 1, and -1, 5. So you can kind of see it's coming down from up here pretty sharply. And it does something like this. And my line is not perfect, but at least it's close, and that's kind of what we're looking for. Something of this nature, okay? So this, of course, is an exponential decay because of how my base looks, right? This base being a fraction means that I will be decaying. My function is decreasing, okay? And they mention that up here, right? So if a is between 0 and 1, if it's a fraction, you're decreasing. And vice versa. If we had a whole number, then this function is, of course, going to be increasing, okay? So just some points to remember and think about. Okay, so on this next example, we're kind of going to do some graphs with the transformations, and let's compare it based off of the original graph, which is just 2 to the x power. So first, I'm going to list the 3 points I would use for 2 to the x power. Okay, so 2 to the x power, I would have something like this. How about -1, 1/2, right, which is 1 over 2. And then 0, 1, of course, my classic y-intercept. And then we're going to also have 1, 2. And if you want to project further, yeah, 2, 4, 3, 8, whatever, you can plug in some extra points. But these are kind of my basic starting points that I'm going to rely on. And what I'll do is let's go ahead and sketch these on all 3 of our graphs. Okay, so with these parent functions, I just roughly sketched what it looks like. I wrote those 3 points and kind of connected it with a graph arrow going upwards. Okay, so let's see if we can kind of dive into these and see, and some of them are not necessarily the greatest sketches, but we'll start with A, and you can see that A is a reflection, right? This is a reflection over the x-axis. And so we can just take the points that were given and flip them over the x-axis. So here we go, we've got a -1/2 here, a -1 here, -2. And if we wanted to go further, we can, but it's something like this, right? That point is not necessarily the greatest sketch, but there we go. Something like that. And this is, of course, just taking the point and reflecting it over the x-axis. Make that a little nicer. Okay. And so now let's take a look at problem B. Okay, so that says x plus 3 in the exponent. Okay, so that one can be a little bit tricky. It's hard to visualize sometimes what's going on here. But if you have 2 to the x plus 3, this plus 3 right here, guys, is actually going left 3. Okay, so anything that's up in that exponent is a left-right shift. And specifically in this case, it is going left 3 spaces. Okay, and so we can just take the basic points that we've had, these -1, 1/2, 0, 1, and 1/2, 1, 2. We will take those and just slide them to the left. So here we go, something like this. So right here, that one is right there, maybe something like this. Okay, so again, just taking my exponential graph that I already had and just kind of sliding it over there. Okay, and our last one has two shifts, so let's take a look at what that one looks like. It says 2 to the x minus 2 and then -1 at the end. So let's see what those transformations are. 2 to the x minus 2 and then -1. So in this case, we've got two moves. We're going right 2 spaces and down 1. Okay. And so again, take these same starting points that we've been using, this same blue graph, and let's just go right 2 spaces and move it down 1 space. So I'll start at this 1/2 point. We'll go right 2 spaces and then down 1. So maybe like -1/2 there, and then there, and something like this. And so you can kind of see again, what I'm doing is plugging in as best I can where these belong, and then just connecting it with this exponential line, okay? Remember, it's going to rapidly start to rise. If you plug in even one extra point, you're going to see, wow, this slope shifts up pretty tightly. So like if you plugged in 2 and you got 4 as that last number, you're going to see, hey, this graph starts really taking off pretty quickly. 2, 4, and then 3 is suddenly at 8. 4 is at 16, and you're just flying up that y-axis, okay? So this is basically how I would approach graphing any of these functions, right? I would say, hey, I'm going to use my starting points right here, and I'm going to just try to adjust them based on whatever transformations I see in there. Okay, let's solve some exponential equations. This is where kind of the good stuff happens and what most people are interested in about this, okay? So there are a few different ways to solve exponentials, and the most basic way is to use a common base, which basically means I need to somehow get these both sides to be in terms of the same base. So let's just try this. I'm going to start by saying, well, 1/3, that's obviously based off of 3. And I can use 3 to also get to 81. So first I'm going to turn 81 into 3 to the 4th power. And 1/3 can be 3 to the -1, also to the x power, like that. Okay, and that is because 1/3 to the -1 is equal to 3. And so let's now do this. We'll combine these two exponents. So 3 to the -x equals 3 to the 4th. And because of one of our exponent properties, we know that if you have the same base, these have to be the same exponent. Now, some people think about it in a bunch of different ways. Some people just think like, oh, you can cross the bases out now that they're equal. But it's a little more complex than that. But that's good enough for us, really. So if -x equals 4, x is, of course, going to equal -4 here. Okay? So what's the idea here? We're saying, hey, if I can get these bases to match up, then I know that these two exponents will be equivalent. So whatever is up there in the exponents, in this case, -x and 4, will be equal, and we can solve it and get a final answer. Okay, let's check it out with something a little more involved here. Nothing really too different, but I see 2 and 8 here as my bases, and I can write both of those in terms of base 2 now. Okay, so what I'm going to do is I'm going to say, well, let's leave this left side alone, 2 to the x plus 4. But on the right-hand side, 8 can be written as 2 cubed, and I'm going to put that to the x minus 6 power. And exponents that are connected like this, exponents on top of exponents, multiply. So this is 2 to the 3x minus 18. And that is still equal to this, 2 to the x plus 4. And now, once I've made this equivalence, we can say this exponent and this exponent must be equal. Okay, again, once your bases match up, you know that the two exponents are equal. I always say this phrase, equal bases, equal exponents, right? When you have the two pieces matched up. And you can actually use this the other way. If you see like x squared is equal to 16, you could say like, hey, well, that's just what? X squared is 4 squared. And therefore x must equal 4, okay? But let's go ahead and solve this one out now. So let's go ahead and say we've got what now? From here, I've got x plus 4 is equal to 3x minus 18. And we can use some clever algebra. I'll just subtract the x to this side. And we've got 22 is equal to 2x. And so I would find something like x equals 11 in this case, okay? And it's kind of a good point that we should be kind of careful to check our work, but we can just plug it back in and make sure that, hey, both sides do work out the same way. Okay, let's take a look at example 6. And what we're going to discover here is there is a little bit of caution we have to take, especially when we have exponents that are even, okay? And this fraction is an even exponent, so let's kind of be wary of that. And so the simplest way of doing this is, let's say, well, x is raised to the 4th power, but under a 3rd root. So I'm going to put the root inside of the power, okay? Cube root, okay? And we're going to put this whole thing to the 4th power, okay? And what we need to do is now say that that, of course, is equal to 81. And let's just kind of work this backwards. And so let's do a 4th root to cancel this 4th power out, okay? And this is where that caution needs to really come into play, because the cube root of x is now the 4th root of 81. And some of y'all might say, well, that's just 3, isn't it? But just remember, it's also -3. So that's kind of the cautionary point. Even exponents lead to plus minus answers, okay? So I'll make a note over here. Even exponents lead to plus minus, okay? And that's just because it's just like when we took roots, right? Square roots always have plus minus in front of their solutions, and so we need to make sure that we kind of capture that same thing, okay? And now let's go ahead and finish solving this. So what will we do here? Let's cube both sides. So that cube will cancel this out. And x equals plus or minus 27. Okay. So just something to be wary of. Beware that, hey, I can get plus or minus when we take a 4th root or a square root or something. And basically, if you see an even exponent in your equation when you're solving it, yeah, you should be kind of aware that this can happen. Okay. And so whenever I do this, we kind of try to handle this root portion first, but you can go in either order. If you wanted to do the cube root and cube both sides first, you could. The only frustration with that is, of course, 81 cubed is a gigantic number, and so I would not really want to deal with that, okay? All right, this is everyone's favorite piece coming up, compound interest. So compound interest is one of the most applicable ways we can use exponential functions, because everyone here has a bank account and everyone here wants to earn some interest in it. So this formula that's given to us, a equals p 1 plus rn tn, is the basic compound interest formula, okay? And just very briefly, we'll mention what these variables are. So A is your current amount of dollars, okay? P is the principal amount, so how much money you put into the account to start. R is your annual interest rate, so that's always based on 1 year. N times per year, so however often the bank is going to calculate your interest. And then T is, of course, time in years that have passed by, okay? So let's check this out. Let's solve a problem with this. So we've got $1,000 deposited in an account paying 4% per year, compounded quarterly. So in this case, I'm just going to make a note here. N equals 4. So quarterly, 4 times a year, boom. That's how we do it, okay? Let's fill in this formula for each of these. Find the amount in the account after 10 years. No withdrawals. So they're saying we just didn't play with it. We just forgot about it for 10 years. Okay. So my current amount is going to be A equals $1,000. 1 plus 4% is my rate, and I'm going to put it as a decimal. We must use our rate as a decimal. And over 4 times, and to the 10 times 4 at the top. Okay, so note again, my n was 4 and my t is 10. And so what's kind of interesting to note is if a lot of people think they're like, well, you know, if I gain 4% per year, $1,000 should be like $40 a year. But it turns out to be more than that because the bank is calculating it more often than just every year. Okay, so if you were to start to work this out, okay, the simple way, like if you were asking me, how would you do this, especially because we work with kind of baseline calculators, I would do this first and get something like 1.01 when I did this to the 40 power. And then I would multiply that by 1,000, okay? And you will get something along these lines. You would get $1,488.86, okay? And so that is the answer to part A. Now let me ask you, how much money did this account actually earn? How much interest did you actually earn in this 10-year period? Well, what would be the easiest way to figure that out? So if this is the answer to part A, okay, well, part B is just take 1,000 out of here, the amount that you started with, and you get, well, you made $488.86, okay? So this is the answer to part B, which is saying how much interest did you earn? Well, you made $488.86. And this is a pretty simple application of the compound interest formula, okay? So just keep in mind what you're going to do when you calculate stuff out. Really focus on that second half first and then multiply your principal at the very end, the p-value. So work out the inside of that parentheses, then do 1.01 to the 40th on your calculator, and then multiply it by 1,000. That's probably the most mistake-free way of doing this. Okay, finding a present value. So this is, again, we're going to rely on that compound interest formula, but the goal is a little bit different, but we can still kind of follow the same logic to help us with this, okay? So Becky must pay a lump sum of $6,000 in 5 years. So basically we're saying Becky needs to come up with $6,000 in 5 years. And so there are a couple of approaches to this. Well, you could say, I'm going to start saving now so that I have this money in 5 years. And so for part A, the first way to do it is they're saying, how much should you deposit if you get 3.1% interest compounded annually to grow into $6,000 in 5 years? So let's set this up. So I know the answer is $6,000, and it is going to be equal to however much I deposit times, so I'll just make a note, this is part A, 1 plus 0.031. Oh, yes, okay, over, and they said this compounds annually, so annually is only n equals 1, okay? And this is raised to, of course, our 5 years of time times the n equals 1 again. And so how are we going to solve this? Well, let's kind of work our way backwards. We're trying to solve for p. So I'm just going to lead with, let's calculate this out. So what is 1.031 to the 5th power? Okay, and that times p is going to equal 6,000. And we'll just come to the side over here and finish this off. So p equals 6,000 divided by 1.031 to the 5th power. Put some parentheses so it's easy to read. And if you use your calculator to work this out, once again, I would use something like your stored memory function to help you with this. Do the exponent part first, then do 6,000 divided by that number. You would get this, 5150.60. So if you deposited $5,150.60 today, in 5 years you could have $6,000 to pay off whatever debt or issue that you have. Okay, all right. And let's take a look at section B as well here. Okay, so section B, a little bit different, but same kind of concept. You only have $5,000 to invest. What interest rate do we really need so that we can earn this $6,000 over the 5 years? So here we go. Here's 6,000 equals to 5,000, okay, 1 plus r, some unknown, over 1 to the 5 times 1 power, okay? And this one's a little trickier to work around, and when we progress further into this, we will talk about more advanced techniques that let you solve this in more efficient ways, we should say. Okay, so as we progress and talk more about exponentials and their inverses, we'll see some better ways to solve this. But for now, let's work through this. Okay, so first, let's simplify some of these pieces. So this piece right here ends up being 1 plus r to the 5th power. And that's equal to 6,000 divided by 5,000. Okay, so basically I divided this 5,000 over and I simplified this piece. And so basically these cancel out. All these zeros are going to go away. And so now to get rid of this 5th power, what we'll do is we'll come over here. I'm going to go ahead and say, hey, now I've got 6 over 5 to the 1/5 is equal to 1 plus r. And then we subtract 1 to get our final answer. So 6 over 5 to the 1/5 minus 1 equals r. And if you solve this out, you would get that the rate is 0.0371 or 3.71%. Okay, and so as we do this, you're seeing like, okay, you know what? I needed to find certain pieces of this equation, and we went ahead and solved back for them. The most challenging part about this is not actually the algebra, it's just actual computation, because things like 6 over 5 to the 1/5 power can be kind of tricky, especially when you don't have fancy gizmos or calculators to help you with it. So just be very careful when you solve these out algebraically. Make sure that you are punching your numbers in and you're double checking your work and making sure that everything works out right. Okay. But essentially, whatever the missing part of this formula was, we just worked backwards to solve for it. Okay. Now, moving on to the value of E. This is a very interesting one. Okay. So E is a very powerful constant. And it just kind of pops its way up into a lot of different places. But this is the sequence where it originates from. And so this is included in our notes because I just wanted to show you the origins of this. And it basically imagines, hey, what about a situation where I'm doubling, but I'm compounding at this rate where both this piece and this piece are increasing, right? So imagine what's happening here. So if we look at this kind of separately, and it's just kind of an interesting study point here. So as n increases, so this exponent increases, but this piece is going to make the entire fraction here decrease. So, like, what's happening here, right? This section is going towards 1, and the exponent is going towards infinity. So, like, what actually happens? We know that if it actually was equal to 1, well, 1 to any exponent would equal 1. But instead, because it's not quite 1, what happens? Well, you can kind of see the progression along this series, and you can see that it starts to approach 2.71828. And you can progress it further. E is actually irrational, so they've kind of given us a lot of digits of it here, but you can see that it continues forever. We should say, like, hey, this is a ... kind of situation, right? ... So just kind of a cool idea, but it applies to a lot of things, and the main one that it's going to apply to for us is going to be what we call continuous growth, right? And that just essentially means, what about in a situation where we don't stop to check how something's growing, right? It's not checked quarterly. It's not growing quarterly. It's growing every second, every moment that it's there, okay? And this applies to a lot of different phenomena that occur in nature. So let's see an example here. So here is our continuous growth formula, and it's sometimes referred to as continuous compounding. And so P and A are, of course, our starting and final amounts. E is that constant that we know. Your calculator should have an E button, but you can also approximate E as 2.718 if you want, okay? But use your calculator button if it has one, okay? And then R is, of course, the rate as a decimal, and T time, okay? So let's see what we've got. $5,000 is deposited in an account paying 3% interest compounded continuously for 5 years. Find the total amount on deposit at the end of 5 years. Okay, so let's just set up our formula and see. This one should be pretty simple. So how much is in our account? $5,000 times E to the 0.03 times 5, okay? And again, this is just a pure computation at this point. So yeah, sure, if you're not 100%, be very careful plugging this into your calculator. But otherwise, there's not much beyond that. We've got 5809.17, okay? And that's basically how much money you've got. And this is, of course, going to be higher than any compounding number that you could put on it. All right, so if you compare this to compounding daily, monthly, hourly, yearly, so on, you will find, yeah, this is definitely higher than none of those, okay? And that's actually our last piece for this, is going to be comparing what is the difference if we compounded different periods, right? So we can see, like, hey, what if we compound at n equals 1, once a year, twice a year, so on. Let's just set up our formula and kind of see what this one looks like. And in this problem, they say $1,000, 4% quarterly, compounding for 10 years grows to 14,886. We saw that already. Okay, that was 4.27. And we're just basically going to change the compounding rates and just see kind of what we get. So I'll just show you the setups for each one and how much we get. So if we did something like this, your amount is 1,000 times 1 plus 0.04 over 1 times 10 years to the times 1 compounding period. You would get, this is 1480.24, okay? If we do the same thing, but now we compound it semi-annually, okay, so this is twice a year, so 10 years times 2, you get something like this, 1485. Oops, skipped a number here, 1485.95, okay? And what I'm going to do is I'm going to write out the other ones, but basically it's the same general idea. All we're doing is we're kind of filling in the different compounding periods for it. And here I went ahead and filled in the remaining values, and you can kind of see, so like this is like every year, so this is like once per year, this is twice per year, this is every quarter, 4 times per year, 12 times per year being monthly. This is 365 times, and I hope you guys know that's how many days are in a year. And then finally, our continuous growth. So you can see, as you check more often, as you increase your compounding period, this number starts to increase, right? Each time you're earning more and more in your bank account. And the simple answer to that is, of course, the more oftentimes you compound, the more times your thing has been exponented. So even though you are dividing that interest rate into smaller pieces, you're getting more out of it, okay? The continuous growth, of course, is going to be the highest one that you can reach, because it is saying, like, hey, I don't stop to check it ever. It is just going at all times, okay? And if you really wanted to come up with how they get that, you need some tools that you would learn in calculus, okay? But Guys, that is the end of chapter 4, section 2, exponential functions. Okay. The interest formula is just one of the most common ways we see exponentials. There are a lot of other ones that we run into. Things like sound. The way we measure sound is on an exponential scale, the decibel scale. Things like how bacteria grows, how population grows, spoiling of food, viruses spreading. All of those follow exponential growth or decay models. And so that's why it's important for us to understand this. Okay. Well, as always, guys, good luck and happy studying.